Next talk, as we see, is by Jakob Müller-Hill, and he will speak on hyperbolic Hubbard-Stratonovich transformation.
So first, thank the organizers for giving me the opportunity to talk here. And the talk is about hyperbolic Hubbard-Stratonovich transformation, and the work I'm going to present is joint work with Martin Zirnbauer. Hyperbolic Hubbard-Stratonovich transformations are, for example, used in the derivation of nonlinear sigma models, as we have seen of them quite few today. Let me give you a brief outline of the talk. So first, some motivation, where these Hubbard-Stratonovichs are used, and then I will spend quite some time talking about these Hubbard-Stratonovich transformations, especially why they are non-trivial in the hyperbolic case, and so what is known about them and what are the recent results. Then I will just explain our new results and give a sketch of the proof, which will also explain the geometric motivation behind this. Yeah, as I already mentioned, these Hubbard-Stratonovich transformations are used in the derivation of nonlinear sigma models, for example, in the derivation of the supersymmetric nonlinear sigma model. And so what's the scheme, or what are the main steps? First one represents the objects of interest, so product of Green's functions, which can be rewritten as some ratio of determinants, as Gaussian integrals over some supervector field phi. This is done to be able to perform a disorder average. And then, as a next step, one wants to introduce good new variables. These variable supermatrices Q, which are conjugate to some tensor product of the supervector field phi. S is here a diagonal matrix with plus and minus 1 on the diagonal, which just corresponds to the Green's functions being retarded or advanced. So each phi A is here a vector, and here this S matrix acts on this. So this step is done to be able to perform the integration over the phi, and then one goes on with the saddle point approximation. The whole talk will be concerned here with this step, this introduction of a supermatrix conjugate to this tensor product. And the method is Hubbard-Stratonovich transformation. So there are different methods, but we will concentrate in this talk on the Hubbard-Stratonovich transformation. Since all the non-trivial things just turn out in the boson-boson block, we will restrict to the boson-boson block. And for the same reason, we can also restrict to the zero-dimensional case. So the starting point will be an integral like this over this vector field phi. Now there are no anti-commuting variables anymore. Here, this A is just quadratic in this vector field phi. A is some kind of orbital index. Ij are here the matrix indices, and S is this diagonal matrix with plus and minus 1 on the diagonal, just as introduced on the slide before. So then this integral has here a quadratic part. B is some parameter matrix and some quartic term. The aim is to perform the integral over the phi, and this can be done using a trick called the Hubbard-Stratonovich transformation, or the transformation, where you just replace this quartic term, which prevents you doing the integral, by introducing auxiliary integrals over this matrix Q. So, and these auxiliary integrations just linearize this term. By introducing these auxiliary integrations, you can linearize this A term in the exponent. So then the integral is quadratic in the phi's, and you can just perform it. So now the question is, where's the non-trivial part of this? And because this just looks like a simple Gauss integral here, and indeed you may just call it a Gauss integral. And so you just say it's a higher dimensional generalization of this one-dimensional trivial integral. But
We're missing here. E minus b squared.
Yeah, there's a square missing. Yeah. But the problem which might turn out is that you want to exchange integrations. You want to do the phi integration. And if I put here the phi integration, you see that there can be a problem if you want to interchange these integrations. Because this term here, the cross term between a and q, might become unbounded when doing the phi integral. So eventually, there's a problem. And we will discuss this problem for the rest of the talk. And namely, I will show you that a situation where for the standard choice, so the trivial generalization of this integral, this does not work. You can't interchange this integration. And then we will discuss different choices for domains of integration where you can do this interchange of integrations. So, and since we will be considering this integral for the rest of the talk, is written here for your convenience, but I'm sure you can remember it. So let's have an example. And so an example is pseudo-unitary symmetry, where the matrix A is just defined as follows. These phis are now just vectors with complex entries. And S is just this diagonal matrix with plus and minus 1 on the diagonal. Note that in the generic case, that this A times S is a positive matrix. Now, this matrix S has this kind of symmetry. You can complex conjugate, transpose, and then conjugate with this matrix S, and you obtain the same matrix. You can also formulate the symmetry as just saying A is in I times the pseudo-unitary Lie algebra. So if you have an additional minus here, this is just a Lie algebra definition. Since we want to, in the following, I want to introduce a general setting, I will use this general notation. So this pseudo-unitary Lie algebra will be in the following called G. And of course, you can decompose this in a 2x2 block structure. So the K part, which is block diagonal and anti-Hermitian, and this off-diagonal block part, which is Hermitian. And then let's consider the standard Gaussian flat type of integration and see that the problem arises. So I will call this Euclidean in the following, just because you might call this integral just Gaussian, and just now referring to these flat domain of integration, I will call this Euclidean just to prevent confusion. So of course this has to be chosen such that this term generates convergence, is convergent. And this is the case if the Q matrices are Hermitian. So now here we have anti-Hermitian matrices. This is our parameter space for the parameterizing the domain of integration. These cases are anti-Hermitian, so we put an I in front, they are Hermitian. We have the P matrix, they are Hermitian, so we can just leave them here. And then this is my cartoon for this domain of integration, which is all very trivial in a way. And so okay, here are these directions just pointed. GC, I just mean the complexified Lie algebra, which is in this case just all complex matrices. So these are here, and we can view this domain of integration just as a surface in this higher dimensional complexified space. So since we will be considering different domains of integration, this is some of the setting. Now, to see that we get this problem, that we cannot exchange the integrations, take A, which is living in I times the pseudo-unitary Lie algebra, in IP, the IP part, and I times the off-diagonal Hermitian part. So now with the I, it's anti-Hermitian, and take the Q part in the off-diagonal Hermitian part. Then you can see that trace A times Q splits out an additional I, so it's imaginary, so the whole exponent is real. And then you get this problem. Then you have good directions which converge, and you have bad directions which diverge. So this cross term here produces problems. Now this problem of choosing now a different domain of integration D, for which this formula holds, and you can exchange the integration, has been solved in 1980 by Schäfer and Wegner. And the corresponding domain of integration is called Schäfer and Wegner domain. So what is done here? You again have this block diagonal anti-Hermitian part. Put an I in front, you have an Hermitian part. This is a good convergent direction. But then here you take this matrix S and conjugate with the P part. There's an I in front, which is needed, and you have B, which should be positive and real. So you have, in fact, a whole family of domains of integration here. I will not show you the proof that for this formula, and I will not show you that then this problem does not arise because I'm interested in another domain. Let me just briefly comment on the cartoon. So here, I times S is in K. So I times S is somewhere here, some offset. And then the conjugation with P just moves you into the P part here. So therefore, this cartoon, some justification. Well, there's some rigorous proof which goes along the line for the standard Gaussian integral, namely you complete the square of this integral here and then apply an argument of shift of contour. Somehow this domain of integration, though a rigorous proof is available, has not been used much in the community. And this might be due to the fact that it is not stable, so it does not have a full symmetry of the original problem. It's not stable, K is not stable under conjugation with pseudo-unitary matrices. But of course, so this would be is a solution to the problem. The alternative, which has been used much, was suggested 2 years later by Preusken and Schäfer. And so what did they propose? Take again this I times K direction, which is a good direction, and then directly conjugate with this off-diagonal Hermitian part. This domain of integration has a full invariance property, but somehow they did not give a rigorous proof of this, and it turned out that there are some problems with this domain of integration, so that the results you get are in some cases only true in the large n limit. And this is due to the fact that the domain has a boundary somehow. So I should say this boundary of the domain prevents you from doing just a similar proof as for the Schäfer-Wegner and for the standard Euclidean type, where you apply this shift of contour argument, because you have this boundary, this would produce additional terms. In the literature, mostly a different parametrization, mainly a different parametrization of this domain of integration is used. So I will just show it to you, but I will not use it in the following. The different way to get this domain is just by conjugating real diagonal matrices with pseudo-unitary matrices. And this can be easily seen that this is just a different parametrization by noting that you can diagonalize unitarily each matrix IX living in IK into a real diagonal matrix, and then e to the y times k is a pseudo-unitary matrix, so you have this series of equations, and so this is just the same. You can use either parametrization of this Preusken-Schäfer domain. So now, after having introduced all these things, and after I told you what the problem is, I can tell you what are the recent developments. Namely, that in 2005, Jan Fyodorov gave a rigorous proof for the pseudo-unitary case. So by the way, he's responsible that all this problem came up again, and that he brought this up. So he gave a rigorous proof using semi-classical exactness of the corresponding integral. And then later, he and EY proved the pseudo-orthogonal case, so a case with pseudo-orthogonal symmetry for the 011 case, 021 case, and also the 022 case involving some numerical stuff. And there this identity had to be changed a bit for it to hold. So this is not so there's a subtle mathematical change which has to be involved, which is involved. And then just this year, Fjodorova and Sombauer proved the full pseudo-orthogonal case. So what is what has to be changed about this formula? Well, essentially, it just looks the same, but the real difference is here in the measure. You should not. The message is you should not integrate against the flat Lebesgue measure as a density, but against a volume form. So what do I mean? Choose a basis of G, some basis vectors EI, and DQ is then just the wedge product of the dual basis vectors of the EIs. And this DQ can then be seen as some differential form living on this complexified vector space where all these domains are in. So essentially, I shall just erase these bars here. And my cartoon just now looks like follows. And I had to add this arrows because when integrating such a form, I have to add an inner orientation to the domain of integration. And if you want to have a very simple two-dimensional example, which is directly corresponds to the cartoon case, then I have it here. So just consider the simplest two-dimensional version of this integral, where we have just Q1, Q2 as variables. And then parametrization for this domain of integration can be done using Cosh and Sinch. So we have some parameters R and T varying over all reals. And so this is obviously a parametrization for this domain of integration for these two cones. And also note that this has the orientation as depicted there. So if I, for example, start here and then vary T, I just run along this line and then I go into the direction of R, so I'm going upwards here. So this is just the orientation here, and just the opposite if I'm down here and then this is negative, I move along this line and then I have to go up. So I should point like this, then I go up. So this is this orientation here. This is rather small, so this orientation here. You can directly check that this, should erase the bars here also, that this is true, so just a short calculation. Or, as a different point of view, if you don't like differential forms, you can also take the point of view that you integrate against normal Lebesgue measure and just see this integral as a difference of two integrals. So just that you take the integral over this cone just with the plus sign, and the integral over the lower cone with the minus sign, which is just different point of view. So it is easy to write down for the two-dimensional case, but in the higher dimensional case you have more cones, so I will use the differential form, which is easier for my proof also. Okay, so now I can state the result, which is that this identity using the volume form here holds in two general settings. And this here is a cutoff function, which is a technical thing, since on the boundary you have to prevent this from divergences to arise. So on the boundary. So this is just a technical thing which has to be you have to, which you always have to use when you use the Preußen-Schäfer domain. So this approach is unity for epsilon going to 0. Yeah, the first setting contains the pseudo-unitary case, so you just have exactly the same notation. You have here, yeah, this is just exactly the same notation, but now G can be a general real semi-simple matrix Lie algebra which is closed under conjugate and transpose. And this 2 by 2 block structure comes from a involution, yeah, where K is then just the plus eigenspace of the involution and P the minus eigenspace of the involution. The matrices in P should be Hermitian, and A should be again in I times the Lie algebra, IS should be in K. So this is just the setting, the general setting. And the second setting is a bit more complicated, but this contains the pseudo-orthogonal case, so there you have to consider a 4 by 4 block structure just to have all these, to put this into the framework of Lie algebras. Here you have an additional involution which gives you this additional block structure with tau, and it should commute with the other involution. This composition should be the Cartan involution, which gives you the K and the P decomposition. Tau gives you the plus and minus decomposition. S should be in P minus, A should be somewhere in the commutator of P plus with S, and plus P minus. A times S should be again positive. Yeah, so just if you want to have more examples which fit into these two settings, there's this review by Martin Zirnbauer where he discusses all 10 symmetry classes. So, and eventually all these cases fit into these two settings. And you can do here a little, essentially here's a third setting contained with some minor modification, and all the cases just fit into these settings. Now I want to give you a sketch of the proof, but I won't give you all the detailed formula, but just I want to give you the main ideas and the, as I said, the geometric intuition behind it, and it will be done for the first setting. So, first very rough cartoon version. So we have Preußen-Schäfer, and we have here these Euclidean trivial type. The basic idea is to deform this domain of integration without changing the value of the integral into this domain of integration. Then the formula holds, and so one is finished. But of course, here's the boundary, and this is a natural obstruction just to do this. And the idea is to attach surfaces onto these boundary lines, which do not contribute to the integral, such that you get rid of this boundary problem, and then to proceed with the deformation. Note that these orientation have to fit here to the orientations here. And so attaching half planes like this would not have been possible if the orientations were the same in the upper cone and in the lower cone. So just this is a good thing to know. This is possible. And you can also note that the orientations, induced orientations on the boundary are just the opposite, so that you can really glue them together. Let me just note that it is easier to see that you can do the same scheme for the Schäfer-Wegner contour. Since this does not have a boundary, and the cartoon somehow suggests it, you should just somehow flatten it onto the Euclidean type. And this can also be done. So then you, but we will be concerned with this equivalence sign here. So how do I get to this cartoon picture? And the idea is, well, somehow you have to simplify this expression here, this parametrization. And the idea how to do this is root decomposition. In fact, a restricted root decomposition. So what is done, choose a maximal abelian subalgebra A of the P part. So just think in the example, the maximal abelian subalgebra of the off-diagonal Hermitian part. Then diagonalize the commutator action of A on the Lie algebra. This gives you an eigenspace decomposition. Alpha are the eigenvalues. Now each eigenspace has a K part and a P part, which I denote by X alpha and Y alpha. And you also have always these, if X plus Y alpha is an eigenspace and X minus Y alpha is an eigenspace. And now an element H of A acts as follows. So commutator H, X alpha just produces alpha of H, the eigenvalue times Y alpha, the other element here in P now. And the opposite way, so Hx on Y alpha just produces alpha of H times X alpha. Now, if you also know that Y alpha can be, each Y alpha in P can be diagonalized into this abelian subalgebra using the corresponding compact group which corresponds to the K part of the Lie algebra, then we can insert all this into this parametrization and just after a few lines of computation end up with something we can now concentrate on one eigenspace here. So we have a cosh alpha of H times X alpha plus sinh alpha of H Y alpha, which is essentially, if we for simplicity assume now that the eigenspace is one-dimensional, just this kind of thing. Now, the real situation is so I will proceed now, but let me note that in the proof we had to do a little bit more work since H acts simultaneously on all eigenspaces. So you have to be a little bit more careful. But essentially, the idea is do root decomposition and then use the two-dimensional situation as in the simple example there. Next step would be attaching the half planes. And, oh, well, no, I have still an additional picture here. And the picture contains the following additional information, which might not be obvious at first glance, namely that the boundary now here is given by these eigenvectors. So if you do the limiting process of H going to infinity, somehow rescale, then you get X alpha plus minus Y alpha here as boundaries of this cone. Now, the attaching of the half planes should be done such that these half planes do not contribute. Just to see that this is possible, let me consider the simplest examples in two dimension. E1 and E2, just basis vectors. Just consider the following surface. T and S are some other parameters. T times E1 plus I times S E1 is of course a two-dimensional surface in the corresponding complexified space. And then just you see that if you insert the tangent vectors into the volume form, tangent vectors are E1 plus I times E1, E1 and I times E1. The volume form is E1 dual wedge E2 dual, and these two are linear dependent over C, so the I pulls in front here, and this is immediately 0. So this is the idea why you have these null surfaces. And if I show you again the picture of these cones with the half planes, attaching of the half planes, you note that this boundary is given by I times G alpha, then it should be immediately clear that the next, so this direction you have to choose for the half plane here. This is I times G alpha, and the other direction should just be G alpha for this to be a null surface. So indeed, in the proof, you can do this, but we had to work a little bit more, since you also have to check that the direction into which you're going is convergent. So in this case, this cross term should guarantee convergent. So we have checked this. And note that this term is important because these eigenvectors here are null vectors. So this quadratic term vanishes for them. And of course, here you need this positivity requirement for A times S being positive. Okay. Now the last step would be the deformation. And just what do I mean by this deformation exactly? So I want to have a smooth mapping from this extended Preußen-Schäfer domain into this Euclid domain. And what do I want to use? So you all know that if you have two paths, gamma 1 and gamma 2, like this, and you integrate them against a holomorphic function, you know the theorem of Cauchy applies, and the integrals are the same. And this can be also seen as a version of Stokes. So the integral over gamma 1 minus gamma 2, this holomorphic function, is just the integral over the surface in between, where you have to apply here the outer derivation d. Well, of course, this is directly 0 because you have only the dependence on z, and d wedge dz wedge dz is 0. Okay, we will use a higher dimensional generalization of this. So note that our function we are integrating here depends holomorphically on Q. So that's the reason why we can do this. So we have some, I put here general arguments. So this is just symbolically phi of some time step E of the extended Preußen-Schäfer minus and so on, some step. You can just integrate over the volume in between, and then you get 0. So that is why you can deform these surfaces. Let me also give you an impression how this is done. So let me give you the two-dimensional cartoon version. Here again, this picture of the extended Preußen-Schäfer domain. And now, the idea is to smoothly project here onto this IK direction, which is convergent. So this would be just these two cones, project them smoothly onto this line here, the IK direction. And then for the attached half planes, you should project here onto the P part. So this would be some K alpha plus P, X alpha plus Y alpha. You should project on the Y alpha part. You should do this smoothly. And then you end up with two half planes being glued together, living in the IK plus P space. And this would be just the standard Euclidean version. So you can see rather directly that this scheme works in the two-dimensional case. So you have, of course, to check that this is convergent and the boundary terms vanish at infinity, that the deformation does not degenerate is clear in the two-dimensional case, but you have to do some work to do it in the higher dimensional case. So this is then the finish of the proof, so I can come to my conclusions. Preußen and Schäfer Hubbard-Stratonovich transformation can be obtained through a deformation of the standard Euclidean Hubbard-Stratonovich transformation using Stokes. And now you can use Preußen-Schäfer in a very general setting rigorously if you use the right volume element. So if you use this volume form. And also that you have a unifying point of view, namely that Schäfer and Wegner, the Schäfer and Wegner family of domains of integration is also a deformation of this Euclidean Hubbard-Stratonovich transformation using Stokes. So the picture is the following down here. And just remember the original problem. We had this identity and we wanted to exchange the integration over d phi and dq. Now this was not possible using the simple Euclidean domain of integration. but it is possible for the Schäfer and Wigner domain of integration, and it is also possible for the Heusken-Schäfer domain of integration. So, and these are, so to say, just deformations of the original domain of integration. So, of course, there are hundreds of thousands identities like this which hold, but there are only a few which have these symmetries and for which you can exchange the domains of exchange these different integrations. So, thank you for your attention.
Okay. Questions? Yeah.
Do I understand correctly? I mean, if I just interpret this picture, that in principle, it seems that there are to distinguish members of this family. I mean, Schäfer-Wegner and Proust-Schäfer. But in principle, there is the whole family of allowed deformations on which this transformation will be, this type of integral will be convergent, and then this means that we can have very different, maybe not that trivially related parameterizations for Q matrices, which maybe in some applications will be useful to have in mind. Is it correct?
First of all, yes, there are many allowed deformations. So already you can see that you can, that it's allowed to deform this thing here into that. You have a vast variety of different surfaces for domains of integration for which this holds, and also for which the integral is convergent. But then you have, of course, to be very careful if the different phi and q integrations interchange.
Yeah, that's my question. I mean, if we also impose, of course, a requirement that we can interchange, then can you say anything about allowed family of these domains? Because we see two, but maybe your calculation suggests that probably there are more, not only two.
Well, on the right-hand side, going in the direction of Schäfer-Wegner, you have
Yeah,
more.
the family.
But I think we should check this. But my feeling is, going to the left, you're always on bad territory, always in bad territory. Only when you finally arrive at Heusken-Schäfer,
only then you can.
fine.
I see.
So you really have to push it to the limit. All the way, it's forbidden, but only when you push it to the extreme limit, then you have again a valid, in the sense of interchangeability.
I mean, that's true, and this is due to this.
You agree with this? You've thought about this much more than I have.
I mean, of course, you have these half planes which move somewhere in an imaginary direction with respect to the others, and I mean, so there's a different term. So if you integrate over the phi's, this should be bad. So and these contributions only vanish in this real limit where you just squeeze this domain of integration really into these cones.
So the bottom line is that basically, again, we have a well-defined Proust-Schäfer, like it stands, and the family of Wegner-Schäfer parameterizations, and that's it.
Yeah.
Okay, thank you.
Excuse me, does it mean that also when you compute things inside the nonlinear sigma model, you should use this measure that you found, not the naive one?
Yeah.
Does it change anything, or?
Well, I mean,
In large and limit, no.
no. If you do the large n limit, as I told in front, so
yeah.
then these boundary, so then only one of these disconnected domains of integration just contributes. And I mean,
So should I say, for example, that if I look at the random matrix problem, which is known how to solve using Godin-Mehta method, and for finite n, in this, with the usual procedure, you would find a difference between the exact result and the new one. But with this measure, I should get even the correct result at finite n.
Yes.
yeah.
Okay. I thought long time ago.
I see. So you
encountered this problem.
If I can testify, personally, I met this problem, and also reading even Shadorov review article in Lesush, I remember.
Yes. Then I did not understand that.
Just at this point, you mumble, well, by analytic continuation, You should have this. And I try to understand this analytic continuation. I even look at the case of 2 by 2, just what you did, and I could not see.
That's why I
so
reconsidered it in 2005.
Okay, so
It was precisely the reason I also discovered
Okay.
it.
Old problem solved.
okay, very good.
All questions? Well, if not, we thank the speaker again.